In this video, we'll discuss grouped data, as well as the wrong ways to analyze grouped data. Hence, we'll explore the limitations of our current modeling toolbox. Now, this topic is important because grouped data is quite common in practice. In particular, it's common to work with a dataset where the rows are not independent, but rather they correspond to different groups. This structure is also often referred to as repeated measures data. Consider some examples. Suppose we're interested in Y, the performance of two different mosquito repellents, A and B. To learn about Y, experiments are performed at multiple labs. Since these labs have their own unique conditions, protocols, and scientists, the outcomes at each lab might be related. That is, these data are grouped by lab. For example, this means that the outcomes at Lab 1 are independent of those at Lab 2, but the experiments within Lab 1 are related. As another example, suppose we're interested in the relationship between running time Y and age. To learn about Y, we observe multiple runners across the span of several years. Since each runner has unique training, experience, and so on, the outcomes for each runner are related. For example, this means that our data are grouped by person. The outcomes for runner 1 are independent of the outcomes for runner 2, but the outcomes within runner 1 are related. Now, there's a reason that group data is so common. Mainly, it's a feature, not a bug. First, group data can improve the efficiency of data collection. For example, to learn about mosquito repellent performance, suppose we wanted to run 1,000 experiments. In coordinating this effort, it would be much more efficient to run 200 experiments at each of 5 different labs than to run a single experiment at each of 1,000 different labs. Second, group data provides within-group insights, that is, insights into the variability within each group. Consider a running example. By observing each runner across the span of several years, we not only get a sense of the general relationship between running time and age, but the degree to which running times within any individual can vary from year to year. Finally, group data provides between-group insights, that is, insights into the variability or comparisons between different groups. By observing each runner across the span of several years, again, not only do we get a sense of the general relationship between running time and age, but the degree to which this relationship might vary from person to person. Next, let's consider the limitations of our current modeling toolkit when it comes to analyzing group data. For example, let Y be the popularity of a song on Spotify, and suppose we want some sense of the typical popularity of a song, the degree to which popularity varies from song to song, and the degree to which popularity varies from artist to artist. To this end, we'll use a set of data that's grouped by artist. For example, our dataset contains multiple songs by Elisa, multiple songs by Frank Ocean, and so on. Now, before analyzing this data, it's important to set up some notation. In total, our dataset includes 350 songs spanning 44 artists. Thus, our notation for song popularity requires 2 subscripts, one to denote which artist we're talking about, and one to denote which song within that artist we're talking about. Specifically, let Yij denote the popularity of the ith song for artist J. Also notice the order of these 2 subscripts. The second subscript corresponds or reflects the group of interest, and the first subscript notifies or denotes the observation within that group. This means that we can think of our sample of 350 songs as the collection of the smaller samples on the 44 artists. For example, these 350 songs are comprised of 19 songs from artist 1, 4 songs from artist 2, on up to 5 songs from artist 44. Also note here that when we have one subscript that has at least 2 digits, then we distinguish between the 2 subscripts using a comma. Using our current toolbox, we might try to model this group structured data using a complete pooled strategy. Represented by the flowchart here, a complete pooled model entirely ignores the grouping structure, lumping all songs together in a single pool. That is, by assuming that what we have is a random sample from the entire population of all Spotify songs, this model incorrectly assumes that the popularity of one song in our dataset is independent of the popularity of any other song. To be clear about why this assumption is incorrect, note that some artists tend to be more popular than others. Thus, the popularity of one song for an artist is related to, not independent of, the popularity of their other songs. To implement the complete pooled model, we can start by assuming that popularity varies normally from song to song, as represented by the plot here. Specifically, across all songs I, for all artists J, Yij follows a normal model with mean mu and standard deviation sigma. Note that this model depends upon two unknown parameters, mu and sigma. Thus, to complete our Bayesian model of song popularity, we can place prior models on these parameters. But to really understand these priors, we have to first understand the meaning of the parameters they describe. In this model, mu represents the global average song popularity, where global means the average popularity across all songs and all artists. Further, sigma describes the global standard deviation in popularity. That is, it describes how variable popularity is from song to song, again across all artists and all songs. Again, the complete pooled model strategy incorrectly ignores the fact that we have multiple related songs for each artist in our sample. It puts them all into one pool or population. Using our current toolbox, we might instead model this group structure data using a no-pooled strategy. Represented by the flowchart here, a no-pooled model incorrectly assumes that one artist's data doesn't tell us anything about another artist. Thus, that the artists in our sample don't tell us anything about the broader population of artists on Spotify. Hence, we can really only use this model to understand the individual 44 artists in our sample. They're not connected in this flowchart or the model in any way. To be clear about why this assumption is incorrect, though each individual artist is unique, data on other artists can also give us a sense for how popular another artist might be and how much their popularity might vary from song to song. That is, artists aren't totally unrelated. To implement the no-pooled model, we can start by assuming that popularity varies, normally, from song to song within each artist. That is, as represented by the plot here, each unique artist has their own unique normal model. For example, for artist J, the popularity of different songs I, that is Yij, these Yijs follow a normal model with mean μj and standard deviation sigma. So again, these individual artist-specific models depend upon two parameters, μj and sigma. Thus, to complete our model, we can put priors on the parameters. Yet to understand the priors, we first have to understand the meaning of the parameters they describe. In this model, μj represents the artist-specific average song popularity. For example, μ1 is the average song popularity for artist 1, μ2 is the average song popularity for artist 2, and so on. Thus, the models, or the individual models for each individual artist, they get a unique mean. And one artist's mean doesn't tell us anything about another's. Further, as represented by the plot here, note that we assume in this particular model that all of the normal models for each individual artist have the same standard deviation, sigma. That is, sigma describes the standard deviation in popularity from song to song within each artist. It gives us a sense of how variable a single artist's songs might be, not just the variability across all songs on Spotify. Further, though we're assuming for simplicity here that this variability is the same for all artists, thus, the width of the normal model is the same. We could also put a J subscript on sigma, thus assume that the variability in popularity is artist dependent. That is, we could assume that some artists experience more variability in popularity from song to song than others. To recap, a complete pooled model ignores the grouping structure and lumps all songs together, incorrectly assuming that the popularity of one song in our dataset is independent of the popularity of any other song. Swinging the other direction, a no-pooled model builds a separate model for each artist, incorrectly assuming that one artist's data doesn't tell us anything about another artist. These artists are not connected. A hierarchical or partial pooled model provides a sensible middle ground between these two extremes. The strategy here is to not only acknowledge, but to harness or utilize the grouping structure of the data. First, unlike the complete pooled model, a hierarchical model correctly assumes that songs within each artist are dependent. That is, the popularity of one song for an artist is related to the popularity of their other songs. This idea is reflected in the lower levels of our diagram here, which groups songs by artist. Further, unlike the no-pooled model, a hierarchical model correctly assumes that data on one artist contains valuable information about other artists in the sample, as well as information about the broader population of Spotify artists. This idea is reflected in the top level of our diagram here, which connects all artists by the population from which they were sampled. Now that we've motivated the need for hierarchical models, we'll explore the details of implementing this technique in class.